Alright, so let's have a look here now from the passage. This passage is a little difficult, a lot going on, big compounds dealing with. I drew up one up here. This is silanandramide. Fairly large compound, pretty complex, but as you probably notice in the passage or doing the questions, not too much to deal with it. Just having a quick look at the passage, like so many organic chemistry passages, the pictures are worth much, much more than the words themselves, and the pictures help us solve a lot of clue. In particular, figure 2, the schematic scheme, is our big help with this one. I didn't write it all up here. We'll look at the important points as they come across, but hopefully use that much more in reading. So, typical MCAT passage, first paragraph really is like reading a Wikipedia article, a little summary of what's going on there. Passage 2 starts to talk, or paragraph 2 rather, starts to talk about the actual reaction and what's going on here, and then they go into a little bit of detail about the compound 6 there that we're looking at, which I drew up here on the bottom because we'll use that a little bit later on too. But overall, hopefully you see the important part of what's going on in the reaction scheme, and we'll talk about it as we go through the questions here. Hopefully you were able to think big concepts, big picture, not get bogged down. Of course, you're probably not going to know this reaction off the top of your head. You probably wouldn't guess this schematic off the top of your head. Remember, the important part of what the MCAT's asking for here is, can you tell us from one compound to another how we got there? Could you call it label it a type of reaction? Could you explain what's going on? It's not, did you know how to go there? So let's keep that in mind as we go forward. Don't get bogged down again in the details of mechanisms. So, question 1. If the Des-Martin pyridine was used in step 2, was not available, which of the following reagents would serve as a substitute? So for question 1, what we're looking at then, say, okay, step 2. We need to replace what's being used in step 2. So we have a compound here that looks a lot like, I have this going on. We have some hydrogen sticking out here and here. An OH group sticking out over here. And another carbon over there. And they're saying, okay, we use this reagent, and in the end, gives us a similar looking structure, but a little different. We have some other things going on here. We still maintain those hydrogens. Stereochemistry is still the same for all of our other molecules happening here. We still have hydrogens out of the plane. However, notice our alcohol has now been turned into a carbonyl. So essentially what this question is saying is, if Des-Martin wasn't there, what could we use to turn an alcohol in this carbon into a carbonyl? We're not touching anything else or affecting anything else. So in my mind, what I'm thinking is, what reactions do we know as a whole, because again, think on a large scale, what reactions do we know that turn alcohols into ketones, or in this case carbonyl, just in general? And hopefully what you're thinking is oxidation. We spend a lot of time talking about oxidation reduction reactions. Hopefully this is just a clear picture of alcohol to carbonyl, definition of oxidation. We're losing hydrogens or we're gaining O's. And then as we've kind of learned over the course of a couple lectures here, oxidation. Oxidizing reagents, I told you the quickest kind of rule of thumb to remember here, it's those reagents who have a lot of O's. So let's look at our answer choices. NaBH4. NaBH4 is actually the exact opposite we do. So like we talked about, oxidizing reagents have a lot of O's, reducing agents have a lot of H's. So NaBH4, probably not our best answer here. It's going to give us a reduction, the exact opposite of what we're looking for. Then we get to H2SO4. Now I know I said a lot of O's typically means a lot of oxidizing reagents. But remember, first and foremost about chemistry, everything's related to acids and bases. Hopefully you very quickly remembered H2SO4 is one of those strong acids. Not really looking what we're wanting to do here again. It's just a strong acid. Let it be a strong acid. Yes, I know it has a lot of O's, but hopefully you remember your acids and bases first. So then that gets us down between CrO3 and SOCl2. If you had to guess out of those two, A, based on the number of O's and what they do, hopefully you would pick CrO3. A very good oxidizing reagent in this case. Okay, moving forward. If compound 3 were treated with H2 in NH2, hydrazine is another word for that, with a little bit of base, and the reaction was monitored by IR, the diagnostic band showing the conversion of the starting material to the product would be, so they're saying, okay, take compound 3. look at compound 3, it's this one right up here. So we'll just start that same molecule. And because we're talking about IR, we're talking about functional groups. So yes, we have an alkene as a functional group, and we have carbonyl as a functional group. Alkene, not really a whole lot of interesting stuff from an MCAT purpose. You remember going through organic class, you had plenty to learn about all the different types of bands. But remember, we talked about on the organic chemistry section on the MCAT, we're pretty specific to two things. We like seeing the appearance and disappearance of OH bands around 3,300, and the appearance and disappearance of C-double-bond-O, carbonyls, around the 1,700 region. So what you saw here was, okay, let's treat this material right here with some kind of very strong reducing reagent. You may not know what hydrazine OH do. That's the Wolff-Kishner reaction. It's actually a reduction reaction. But let's say you didn't even know that's what it does. But again, using some of the clues of the reagent, we always talk about reagents with a lot of H's, reduction reactions. So that's another clue here. So let's start with D, appearance of a CN stretching frequency. CN. If you'll recall, we really only focus on the double bond O and the OH. So let's just say, let's put that answer to the side. I won't say it's completely wrong, because you don't really have any information, although we talked about on MCAT, they're very rarely asking anything else besides carbonyls and alcohols. The appearance of the CH frequency. Remember, C single bond to H is garbage to us. That means absolutely nothing for us. We should never be putting that. Disappearance of the C to C stretching frequency. Again, this is one of those we don't really talk about. You may know the Wolff-Kishner, but it's not going to affect that C double bond C anywhere, anything. It's just a reduction reaction. And that leaves us with A, the disappearance of a C double bond O frequency. Of all the answers, this is the only one we ever talk about in class. It's the only one that I continue to tell you comes up over and over as one of the important ones. Being that it's a reduction reaction, it would even make sense then that, yes, this would disappear. We would no longer have that stretching. And then maybe the secondary question, or another way this question could have been asked, around what frequency would we have seen a disappearance? Remember, those carbonyls disappear around 17 and appear around 1700. Great. So we have our answer A. Okay, finally we get to question number 3. Question number 3 says an ACL tetrameric acids have pK values ranging from 3 to 3.5, making them more acidic than most carboxylic acids. The most stable form of these functional groups has the enol tautomer as a central amide. So let's go over here. Let's draw the structure out. See lots of good things going on here. An alcohol, some carbonyl, double bonded O, in a couple different spots. R groups, R groups. Great, so the first bit told us some interesting stuff. That's nice. Of the following, which explains why the enol, wow, they're even telling you here that the enol version, here's our little enol, our enol version is more favored. Why is that? Well, if you recall, we had a previous lecture where we talked about ketones and enols going back and forth. And I said 95% of the time you're going to say keto is more stable because it's the thermodynamically more stable favored product. All but 2 times we say that the enol is favored. And if you recall, the 2 times we said the enol is more favored is when you have an increase in intramolecular hydrogen bonding, or when you have increased resonance. Again, these are the 2 and only 2 times you'll ever want to say the enol is more favored than the keto version. So they're telling you, they're giving the easy part. They're telling you, yeah, the enol is more favored. You tell us why. Your answer choice, only look for one of these 2 things and make sure it's actually right. So let's look through our answer choices. We have A. The enol tautomer allows for less resonance. It says the exact opposite of what we want. We want more resonance. More resonance would always make sense why it's more stable. When the molecule is in the enol form, the extra pi electrons make the molecule aromatic. Don't think so. I don't think there's anything here that indicates aromaticity to anyone. Hopefully, we're all saying that it's not an aromatic molecule whatsoever. The enol tautomer is thermodynamically favored over the keto. Remember, that's the great answer to choose for why a keto would be favored over an enol. This answer is the exact opposite of what we're saying. we would want it to read the keto is thermodynamically favored over the enol, if keto is our actual answer. So that leaves answer D for the one we're going to choose. Let's make sure, though. The OH of the enol, this thing right here, can participate in intramolecular hydrogen bonding, increases in stability because of intramolecular hydrogen bonding. That's a very good reason, and it's saying it can do so with the adjacent carbonyl. I like that answer. We're going to go with that one.